Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this lecture. In this lecture, we are going to study operational model analysis. Operational model analysis is an alternative approach to model parameter identification and distinct from the conventional experimental model analysis. Operational model analysis is based on analysis of the measured responses to find the model parameters of the system, and that is why it is also called output only model analysis. So, in this lecture, we will first introduce what is operational model analysis, then look at what is the motivation and principle of operational analysis. Then we will see why reference measurements are taken in operational analysis, and finally, we will take an example to find model parameters using operational analysis. So, what is operational analysis? So, operational analysis identifies the model parameters of a vibrating system from its response to ambient or operational excitation. It is seen that some structures in practice, they are subjected to random ambient excitation during the service, and operational model analysis relies on measurement of the resulting responses to find the model parameters. So, this is different from experimental model analysis. We have seen that in experimental model analysis, an artificial excitation is applied, often in a laboratory setup, right, and the input to the system is also measured along with the output to estimate the model parameters. So, we have studied experimental model analysis in all the previous lectures, and we saw that we apply the excitation either using an impact hammer or a vibration exciter, and then we measure the excitation forces that are applied, we measure the responses that result, and then we determine the frequency response functions or impulse response functions from the measured forces and the responses, and then we analyze these FRFs or IRFs to determine the model parameters. So, therefore, we take measurement of not only the output, but also the inputs that cause those outputs, right. But in operational analysis, the inputs are unmeasured and only the outputs are measured, and then analysis of the outputs is done to estimate the model parameters of the system. And because only the outputs are measured and analyzed to find the model parameters, this process is also called output only model analysis. So, let us look at what is the motivation and principle for operational model analysis. So, in experimental model analysis, we need to apply artificial excitation, but for some structures applying an artificial excitation may be difficult. For example, structures like bridges, buildings and some other big equipment. So, applying artificial excitation may be difficult and also uneconomical. Another observation is that in many cases in practice, there is a strong ambient excitation that is present. For example, in bridges, buildings and wind turbines, there is a strong wind excitation that might be present, right, which would excite the structure and generate the response. So, without applying artificial excitation, the response of the structure is available, right. Therefore, there is a possibility of exploiting this natural response that is present, right, for finding the model parameters. So, another observation is that the ambient excitation which is present in many of the structures, they are random in nature. So, these random excitations, they excite the modes which are within the bandwidth of the excitation, and therefore, the response contains the information about the model parameters. It is also seen that the ambient excitation is natural and difficult to quantify or measure, because random excitation or the ambient excitation generally acts over the whole structure. Think of the wind loading on a bridge. So, it acts at almost all the points on the bridge, and therefore, it is difficult to measure and quantify the excitation. But the responses which occur, that can be measured. So, therefore, these observations tell us what are the possibilities and what are the constraints, right, in the model analysis of such structures. And the constraints are that applying artificial excitation is difficult and uneconomical, right, and other constraint is that ambient excitation is difficult to measure. However, the possibilities are that for many structures the ambient excitation is present, and it is often random in nature, exciting the modes which are within the bandwidth of excitation. So, that opens the possibility for determining the model parameters from the measurement of the responses. So, operational analysis leverages these possibilities, and therefore, the objective of operational analysis is to measure and analyze these ambient responses and estimate the model parameters of the modes. So, let us look at how the operational model analysis treats the ambient excitation. The ambient excitation is assumed to be void in operational model analysis. So, operational model analysis assumes that the random excitation which is acting on the structures, the natural excitation is void, right, and we know that the white signal has power spectral density which is flat over the whole frequency range. So, it excites the whole frequency range. However, in practice the ambient excitation may consist of a combination of random and deterministic components. Often it is seen that there are some deterministic components also which are or which might be present in the ambient excitation, and therefore, the response also will contain those response due to those deterministic components, right. For example, in case of bridge, there may be periodic components due to the loading applied by the traffic moving over the bridge. In case of wind turbine, there would be random excitation due to wind, but due to rotation of the wind turbine there would be some periodic harmonic components which will be present in the excitation as well as in the response. So, now what is the implication of the presence of deterministic components and how does it affect the assumption of white noise which is made in the operational model analysis. Let us try to understand the effect or implication of the deterministic components through these two figures. So, you can see in the part A of the figure what is being shown is the system, right, the actual system that is being subjected to the ambient excitation, right. So, this ambient excitation generates the ambient response. So, this ambient excitation is the actual ambient excitation acting on the system, and now this may consist of the random component as well as some deterministic components in general, right, and therefore, the response would also contain random response as well as response corresponding to the deterministic components in the ambient excitation. Now, in the part B of the figure, what we see is that what is the implication of the assumption of white noise input acting on the system in case of operational model analysis. Operational model analysis assumes the ambient excitation acting on the structure to be void. So, this assumption amounts to existence of a mathematical filter before the system. So, you can see this is the mathematical filter which converts the white noise excitation into the actual ambient excitation which acts on the system and generates the response. So, therefore, when the operational model analysis analyzes this response, it effectively identifies the model parameters of the combined system. So, you can see this is the combined system which is shown here represented as in the identified system. So, this dotted rectangular block is the block representing the combined system, the combination of the mathematical filter and the system, the actual system. So, when the operational model analysis analyzes the response assuming white noise excitation, it effectively identifies the model parameters of not only the system, but also of the mathematical filter, and therefore, the identified model parameters contain the model parameters of the physical modes associated with the system, but also contains the model parameters of the non-physical modes associated with the mathematical filter. Therefore, one of the challenges in operational model analysis is to distinguish physical modes from the non-physical modes. One of the differences between the operational analysis and the experimental analysis is the fact that in operational analysis reference measurements are taken. So, let us try to understand that what are reference measurements and why they are taken in operational model analysis. So, what are reference measurements in operational analysis? So, therefore, the question is that how to compare the ambient responses at various points on the structure measured at different times to find the relative phase and magnitude. So, in operational analysis we measure only the output responses, and generally for a large structure the responses may have to be measured at a large number of points. So, generally the measurements are taken in batches. So, we take measurement at certain number of points and then repeat the process to complete measurements at all the points. So, therefore, measurements taken at different instants of time they correspond to different state of motion of the structure. Also, the excitation which would correspond to these measurements would also in general be different, and therefore, these measurements cannot be directly compared to find a relative phase between vibration at different points, right. So, the relative phase and magnitude of vibration at different points cannot be obtained by direct comparison of these responses, right. In case of EMA we apply artificial excitation, right, and we measure also the excitation along with the responses, and then we determine the FRFs or IRFs which correspond to a standard or a common input, and therefore, the measurements at different points they are directly comparable. So, measurements across the test points are directly comparable because what we analyze are the FRFs. Now, this information about relative phase and magnitude of vibration at different points is required to find the mode shapes, because mode shape elements tell us the relative magnitude and phase of vibration at different points. So, that is why it becomes important to see that how the measurements which are taken at different points of time in OMA can be compared. So, this difficulty is resolved by taking what are called as reference measurements. So, what are reference measurements? In OMA we take some measurements which are common to all batches or data sets, and these reference measurements and then are used for normalization of the responses corresponding to different data sets. Let us try to see in more detail what are reference measurements. So, we have two sets of sensors in OMA. One set is called roving sensors, another set is reference sensors. So, what are roving sensors? So, the roving sensors are the sensors whose locations change from one data set to another, while the reference sensors are the sensors whose locations are fixed over all data sets. And we take measurement at those reference locations every time when we take measurements using roving sensors. So, what is the advantage? That once we have the reference sensor measurements which are present along with the roving sensor measurements, then we can find a cross correlation between these signals in a data set, and then that helps to obtain the relative phase and magnitude of the responses in that data set. And then the reference measurement across all data sets can be normalized with respect to the autocorrelation of the reference measurement in each data set. Let us take an example to understand what are roving sensor and reference sensor. So, you can see on this cantilever beam there are measurements to be taken from point 1 to point n. Okay. So, these are the test points at which the output responses are to be measured. So, now we have taken one reference sensor which is fixed at location 1, and then we have another sensor which is roving sensor that will be moved from location 1 to location n. So, when the roving sensor is, let us say, at location 1, then the reference measurement is also taken at location 1. When the roving sensor is at location 2, the reference measurement again is taken at location 1. So, therefore, each measurement of roving sensor is accompanied by a measurement at the reference location. So, measurement with roving sensor constitutes one data set, and each data set we will have roving sensor measurement, and there would be a corresponding measurement at reference sensor. So, let us now try to see that what is the output cross correlation with white noise excitation. So, let us take a multi-degree of freedom system. So, this is the equation of motion for a multi-degree of freedom system subjected to excitation f. So, here now we are going to take white noise excitation at 1 degree of freedom. Let us say at kth degree of freedom white noise excitation x, and then we generate random response at all the degrees of freedom. And let us see what is the cross correlation between the response at ith and jth degree of freedom. So, we will not go into the mathematical details of all this, but we will finally look at that what are the characteristics of this cross correlation. So, the cross correlation between the ith and jth coordinate due to white noise excitation at the kth coordinate. So, you can see this is the cross correlation Rijk, which represents the cross correlation between the response at the ith and jth coordinate due to excitation at the kth coordinate, and it is equal to the expected value of the product of xi t plus t into xj t, right. So, xj t is the response at jth coordinate and xi is the response at the ith coordinate. So, the product of this, when the samples of these two signals they are displaced by time capital T, right, and then we find average value of this, that is the cross correlation. So, we have studied in earlier lecture, right, what is cross correlation, how it is determined, right. So, this is the cross correlation, and so let us see what are the characteristics of this cross correlation due to white noise excitation. So, we see that the cross correlation it consists of damped sinusoids at the damped natural frequencies with their decay rates governed by the modal damping factors. Another observation is that the amplitudes of the damped sinusoids they are functions of the modal parameters. So, this shows that the cross correlation of the output responses when the white noise excitation acts on the system, okay, it contains information about all the modes, right, which are there in the bandwidth of the excitation and which are there in the measurement frequency range. So, therefore, the model parameters can be estimated from the cross correlation estimate. So, these conclusions provide the foundation for the operational model analysis. It says that if there is ambient random excitation, then the output responses can be measured, and then the cross correlation of the output responses contains the information about the model parameters, and therefore, the analysis of the cross correlation should in principle yield the estimates of model parameters. However, it is also observed that these amplitudes of the damped sonoids, they also contain a scaling factor, and this scaling factor is associated with the magnitude of the white noise input acting on the system. So, we see that the this scaling factor, which quantifies the strength of the white noise excitation, that also appears in the cross correlation function. And because in operational analysis the inputs are unmeasured, so we do not have any information about this scaling factor. So, one consequence of the lack of information about this scaling factor is that the mode shapes that are obtained by operational analysis, they are unscaled, right, they are not mass normalized as we obtain in case of experimental analysis. So, the mode shapes are associated with an arbitrary scaling factor. Let us now look at that how correlation function can be estimated. So, we defined an integral definition for cross correlation function when we studied random excitation using a shaker, right. Now, because the measured signals are discrete, we can use a discrete version of the integral definition to find a cross correlation function, and it can be found in this manner. So, you can see here, if there are two discrete signals xi and xj, right, two discrete output responses xi and xj, then the cross correlation between these two is given by this expression, right. So, the two discrete signals, they are displaced by samples m. Now, it is seen that cross correlation estimate based on this expression is biased, because for non-zero values of m, it is seen that there are some terms on the right hand side which are 0, the product is 0. When the two signals are displaced with a difference of m samples between them, then some of the terms in the product, they become 0, which introduces a bias in the estimate. And therefore, an unbiased cross correlation estimate is defined. It is defined using this expression. In operational analysis, we will have responses measured at a number of points. So, let us say there are p number of measured ambient responses. Now, we can calculate cross correlation between any two of these responses. So, we will have p into p number of such combinations which are possible, for which we can find a cross correlation, right. And that is why instead of just one cross correlation, we have now cross correlation matrix RXX. So, it is of order p by p, right. Free vibration response decays with time due to presence of damping, and the correlation functions, because they also consist of damped sinusoids. So, correlation functions are also like decays or free decays. Let us briefly look at what is random decrement. So, random decrement, can also be treated as free decay response. The concept of random decrement was introduced to find a free decay response from a random vibration response, right. And random decrement is an average of the time segments picked up from the signal based on some triggering condition. So, random decrement essentially picks up certain time segments from a random time history utilizing certain triggering condition, and these time segments are then averaged, and that average time histories, it is seen that they correspond to the free decay response of the structure. So, the random decrement dxx tau is defined as the expected value of the time segments x t plus tau chosen when the triggering condition t on x of t is satisfied. So, random decrement essentially picks up the time segments x t plus tau from the random time history whenever the triggering condition t on x of t is satisfied, and the average of all these time segments is taken, and it is seen that this average has a decaying character, and this is called random decrement. So, these free decays or random decrement can also be used to find the model parameters. Let us now look at what are the different methods that have been developed for operational analysis. The Ibrahim time domain method and the eigensystem relation method, they were formulated with free decay responses, and therefore, they can be used for operational analysis. When we studied eigensystem relation method, we saw that it makes use of free decay responses or free pulse responses, and therefore, that method can be used not only with impulse response functions, but can also be used with the free decay responses, right. and therefore, because correlation functions they are like free decay responses, this eigensystem relation algorithm can also process the correlation functions, cross correlation functions, in order to obtain the model parameters. So, that is why some of the time domain methods like ITD and ERA they can be used for operational model analysis. So, there are some other time domain methods like auto regressive moving average method and stochastic subspace identification method that also have been specifically developed for operational model analysis. Some methods have also been developed in the frequency domain. One of them is classical frequency domain approach, which basically is like peak picking method. There is also an approach called frequency domain decomposition and enhanced frequency domain decomposition. These later approaches are based on singular value decomposition. Let us now take a simulated example to perform operational model analysis using eigensystem realization algorithm. So, let us take the case of the simulated cantilever structure we have used in our earlier lectures, right. So, here we assume that the structure is subjected to ambient excitation, ambient random excitation in the form of stationary white noise at different points on the structure. Let us also assume that we are taking measurement of response set at 5 test points, and let the reference sensor is installed at test point 5. So, we have one reference sensor located at test point 5, and let us say that there is one roving sensor that is used to take measurements at 5 test points, right. So, the measurements are taken over a frequency range of 0 to 400 hertz at a sampling frequency of 1024 hertz, and we take a record length of 24 seconds. In operational model analysis, we generally take long record lengths because we need to find cross correlation function, and then having a long record length ensures that the estimates are sufficiently accurate. And as we said, we will have 5 data sets, and this is the summary of measured ambient responses in various data sets. So, you can see we have 5 data sets. So, this is data set 1, and it consists of a reference measurement at location 5, right, and it consists of a roving sensor measurement at location 1. Now, the reference signal that is measured is designated as X51T, right. So, the subscript shows the location of the reference sensor and the superscript shows the data set number. Okay. So, X51 indicates a reference measurement at location 5 in data set 1. Y1T indicates the roving sensor signal. The subscript here shows the location where the roving sensor measurement has been taken. So, Y1 says roving sensor measurement at test point 1. So, in this way you can see we have 5 data sets. So, each data set contains one reference measurement at location 5 and roving sensor measurement at the corresponding test point. Let us look at plot of some of the measured ambient responses. So, you can see we have first of all the 2 plots from the data set 1, right. So, this is data set 1, you can see here this data set 1. So, this is a reference signal. So, it is the random ambient response, and this is the roving sensor signal. We see that the roving sensor signal magnitude is small, that is because this data set corresponds to roving sensor measurement at test point 1, which is close to the clamped end of the beam, right. So, that is why we expect a smaller response there. But reference sensor measurement is at location 5, which is at the tip, that is why the response is larger. Now, these 2 figures at the bottom they correspond to the measurements taken in data set 5. Let us now estimate the cross correlation functions corresponding to these 2 signals in the data set. Because there are 2 signals in the data set, we will have correlation matrix between the reference and roving sensor signals. So, let us look at 2 of the correlation functions in this matrix. This is the correlation function Rx phi x phi, which means that it is the correlation of the reference signal with itself. So, it is nothing but the autocorrelation function of the reference signal. So, this is nothing but this element in the correlation matrix. This is R y1 x phi. So, that is the cross correlation between the roving sensor signal and the reference sensor signal at location phi, right. So, this is nothing but this element in the correlation matrix. Let us now perform model parameter identification. So, now we are going to use the ERA method here, which we have studied earlier. The correlation function matrix of dataset 1 is now used as a matrix of free decays, because we know that the ERA can process the free decays, right, and therefore, this correlation function matrix can be treated as matrix of free decays, and then that can be used to implement the model parameter identification using ERA. So, if you recall, we use the matrix of free decays to first construct the Henkel matrix, right, and then from the Henkel matrix we realize the system matrix or the state matrix A, and then from the state matrix we find eigenvalues and eigenvectors and then the model parameters. So, in this way we find the model parameters using ERA. So, we have seen all these steps in detail in the example when we considered ERA in the experimental model analysis. So, what is the output of ERA? So, for data set 1 we get estimates of natural frequencies, model damping factors, and then we also get part mode shapes. So, these mode shape elements would correspond to only the signals which are present in the data set 1. So, in the data set 1 they correspond to location 1 and location 5. So, we will get mode shape elements corresponding to location 1 and location 5, right. So, this process now is repeated for other data sets. So, the analysis of other data sets also yields the estimates of natural frequency, mode shapes and damping factors for those data sets. Okay. So, the natural frequencies then are averaged over the data sets to obtain average estimate of the natural frequencies. Similarly, the model damping factors corresponding to different data sets, they are averaged to obtain the average value of the damping factor. The part mode shapes obtained for each data set, they are merged or assembled after normalization. So, using the reference measurement in each data set, the normalization of the mode shape element is done and then the mode shapes are assembled. So, that uses the complete mode shape corresponding to all the test points. So, what are the results we obtained for the cantilever structure? So, this table shows the results of the natural frequencies for the 4 modes which are there in the 0 to 400 hertz band, right. So, we can see we obtained natural frequencies for each data set, and at the bottom you can see these are the average values. Okay. These are the average values of the natural frequencies. So, this is for for mode 1, mode 2, mode 3 and mode 4. Similarly, this table gives data about the modal damping factors for different modes and right over the all data sets, and the last row gives the average value of the modal damping factors for different modes. This table gives the mode shapes that are obtained for the 4 modes. This is after normalization and assembly of the part mode shapes corresponding to all the data sets. So, these mode shapes were normalized with respect to the reference measurement at test point 5. So, we should also note that these mode shapes are unscaled mode shapes. Let us finally look at what are the advantages and limitations of operational model analysis. So, one advantage of operational model analysis is that model parameters of the structure corresponding to the actual boundary conditions can be identified. In operational analysis, the test is conducted on the actual structure, right, and therefore, the actual boundary conditions are automatically taken care of. The model parameters which are estimated correspond to those actual prevailing boundary conditions. In experimental analysis, if we have to identify model parameters corresponding to the actual boundary conditions, then that is typically done by simulating those boundary conditions in a laboratory environment, and it is not easy, right, and it is difficult to simulate the actual boundary conditions truly in the laboratory, and therefore, it is always a challenge in experimental model analysis to identify the model parameters corresponding to the actual boundary conditions. But in operational analysis, because test is conducted under actual conditions, the boundary conditions are automatically taken care of. Another advantage of the operational analysis is that the estimated model parameters, they correspond to the actual magnitude of the operational forces. Operational analysis is also useful for large structures, right, where the application of RTL forces can be difficult and uneconomical. One limitation of OMA is that the estimated mode shapes are unscaled, but in EMA we get scaled mass normalized mode shapes. Also, operational analysis requires the presence of some white noise excitation. So, in cases where white noise excitation is not present, operational analysis cannot be used. In this way, we come to the end of this lecture. Thank you.